Hello again. We are going to continue with thermodynamics. So we've gone from work to heat to internal energy, and now we're going to think about enthalpy, which is a function you're very familiar with, but we're going to learn a little bit more detail about the thermodynamics of enthalpy. Okay, so enthalpy. Enthalpy is a defined function, so that means it was defined out of convenience. And the important takeaway is energy transferred as heat at constant pressure is equal to the change in enthalpy of a system. You may remember that. And the reason this is going to be convenient is because most of chemistry is carried out at constant pressure. So constant pressure is more common than constant volume. We'll see a constant volume setup when we do the bomb calorimeter, but other than that, it's pretty common to keep your beaker open to the atmosphere. So if we're at constant pressure, then the volume can change. And if the volume can change, some of the heat that's transferred can be doing work. So that means that all of the heat transferred isn't going to changing the temperature. And that's the important part about defining enthalpy. So enthalpy, by definition, is the internal energy plus PV, so that's equation 1. And we're going to tend to talk about molar quantities, just because then we can take into account how much of a reaction takes place, which is important. So the molar enthalpy would be the molar internal energy plus P times the molar volume. And if we have a perfect gas, we know that for a perfect gas, we take the N over here, we get volume over moles, and so that's equal to RT. So sometimes it will be useful, but remember, every time you write an equation in your note card or use it for a problem, you have to think about when it applies. If it wasn't a perfect gas, you couldn't move from here to here. So a major point to notice is that because H is defined in terms of state functions, so it's defined in terms of U, P, and V, which are all state functions, then it's a state function too. And that means when you think back, Hess's law, combining enthalpy changes to get enthalpy changes for other processes, that is all valid because we've defined it to be a function of all state functions, therefore it's a state function. Enthalpy doesn't depend on how you go from one place to another. It just depends on where you start and where you finish. So good to look at this. So we want to think about why that key point is true, that the heat transferred at constant pressure is equal to delta H. And so if we start out with our definition of enthalpy equals U plus PV, and then we think about changes, change in enthalpy would be change in U plus change in PV. A change in PV can be expanded because if they're all state functions, you could change volume first, holding pressure constant, and then change pressure holding volume constant, or you could change them simultaneously, but it doesn't matter. It should have the same impact on the enthalpy because enthalpy is a state function. So if I expand this, and then I write in the definition of internal energy change, which would be Q plus work. So this is meaning we only have expansion work, no electrical work, which we won't talk about for a while. Then delta U equals Q minus P dV, because minus P dV is, our delta V is work. So when we have these two terms, this one will cancel with this one because we have a positive P delta V and a negative P delta V. And then if we put the restriction of constant pressure, then this term goes to 0 because delta P is 0. And you come up with delta H is equal to Q if the process takes place at constant pressure. So that will be very important for us to think about. And so we've taken Q, which is path dependent, put the restriction on a certain path, essentially, and we come up with a state function, delta H. So that's going to be very, very valuable. Okay, so self-test 2D.1 is not very challenging. Take a look at that. You just have to change the sign because of how they talk about it's released. Then that means delta H is negative. Once again, if heat's released, and in this case, heat at constant pressure is delta H, then it's exothermic, and if heat's absorbed, it's endothermic. So one thing we didn't talk about in Gen Chem is how enthalpy changes with temperature. And it changes with temperature because of this definition. So just like the heat capacity at constant volume was equal to the derivative of internal energy with respect to temperature holding volume constant, the definition, so this is a definition, you can't derive it, you should write it on your note card or a sheet of notes probably. But we can use that to see how H changes. So sometimes the heat capacity is a constant, but sometimes it depends on temperature. It just depends on what range of temperature you're going over. So heat capacity, sometimes these second two terms are not important, but sometimes they are. This equation is just true for non-metallic solids at low temperatures, which you probably won't use that much. But let's just think about how enthalpy changes with temperature based on our definition. So we start out with the definition of the heat capacity at constant pressure is the derivative of H with respect to T holding P constant. And if we want to integrate and think about a finite change in enthalpy and temperature, we take the dt over here, and then we integrate both sides. So we're left with dH, and we have Cp dt. So we're going to integrate from T1 to T2, and from H1 to H2. So this will just be delta H. If Cp is constant, then we can bring it out front, and the integral of dt is delta T. And so enthalpy is going to change as a function of heat capacity is the important thing. If we had to take into account the heat capacity changed with temperature and use the functional form that was just given on the page I was looking at in the book, now I have to do the integral, so the right-hand side will still be delta H, but Cp is this function of T, and so I have to integrate A plus Bt plus C over T squared, and I just had Mathematica do this, and you end up with delta H equals A, so you can integrate these one at a time. This would be a constant dt, same as here, so you'd have A times delta T. The integral of T is T squared. Yes, T squared. So, and the 2 comes out front because when you if you take the derivative and go backwards, it'll make sense to you. So you get all 3 of these terms. So to see how delta H changes if the heat capacity is changing, you'd have to do the integral over that function of your heat capacity. Do self-test 2D.2 and see how much the heat capacity can change. So it tells us to use the equation right here and assume that's how the heat capacity changes. And they ask us how much will the heat capacity change if you change the temperature from 20 to 80 degrees. And we're talking about graphite. So if I look in this table gives me the A, B, and C for graphite. So 16.86, 4.77 times 10 to the minus 3, negative 8.54 times 10 to the 5th. They're all in SI units, so joules. So I'm going to use those numbers. So this is A, this is B times T, this is C, and this is T squared. So A plus B times T plus C over T squared is my heat capacity. So if I calculate it first at 20 degrees, putting in 20 degrees in Kelvin, I get a heat capacity at 20 degrees of 8.31 joules per k mole. If I simply replace the 293 with 353, which is 80 degrees, I get 11.69. So the percent change would be this minus this divided by this. So this would be equal to 41%. So it's not a small temperature range, 60 degrees, but your heat capacity has a significant change. So the very last thing in this topic, so the topic within focus 2 is this relationship between CPs, CPV, CPM, and CVM. So for a perfect gas, the difference in those two is R. Okay, just write it here. So if you have perfect gases, as I said, the difference between the heat capacity at constant pressure and volume is bigger for gases because pressure has a bigger impact on the volume of a gas. So this relationship, Cp, the molar heat capacity minus the molar heat capacity at constant pressure minus the molar heat capacity at constant volume equals R if you have a perfect gas. So we'll start out and we'll look at our definitions. So this is CPM, delta HM over delta T. Then CVM would be delta UM over delta T. And we want to show that equals R. So if delta H equals delta U plus delta PV, and for a perfect gas, if we're talking about molar quantities, then PVM equals RT. We can replace that. So when we go back up here, that means if I put in delta H in terms of U and RT, it would be delta U plus delta RT over delta T minus delta UM over delta T. And this is the same as this. So this minus this is 0. And so you have delta RT over delta T. And R doesn't change. So delta RT is R delta T. And delta T over delta T equals 1. So this just shows you that it's equal to R. So the difference is always positive. So that tells you that CPM is always bigger than CVM. And so if you think about it, if pressure is allowed to change, if pressure stays constant, then you can do work. So if pressure is constant, if you create more gases in your container, in a reaction, for example, then your system can do work. And so now as you're putting heat in, some of that heat is going to do work, and so not all of it is going to change the temperature. So you're going to need more heat put in because you're subtracting off how much is doing work, and the CPM is always going to be bigger than CVM because CVM, all the Q that's put in goes to heating up or changing the temperature of your system because you're not allowing any work to take place. So we will move now on to this is the next section. Now we're going to start talking about things that are pretty familiar to you from Chem 107, how you use Hess's law to deal with understanding how to calculate delta H's if you haven't measured them all.